started. Congratulations for being selected to present your payload, and take it away.
Thank you.
All right. Good morning, I'm guessing it is there.
Yes.
My name is Matt, and I'm here with my colleagues Braden and Dan. We're from the University of Sydney, and today we'll be giving you a review of the USyd Rocketry Team Payload Project Tetratheca. So listed here, we have the main topics we'll be covering. Like all of our research projects here at USyd Rocketry, the payload is named after a native Australian flora genus, Tetratheca, which is shown in the background here.
So for a bit of background information, satellites, when they're launched from their launch vehicle, when they're going up into space, into the orbit, they're imparted with rotational energy. And this rotational energy must be arrested for the satellite to continue its operation, particularly if the satellite is conducting telecommunications and it needs a clear nadir link for downlinking information, or if it's for remote imaging. So satellites, as have been the traditional case, have been fitted with an attitude determination and control system. Now, this system may be an active or a passive system, but its critical and fundamental role is to reduce that rotation and control the orientation of the satellite until it is stable. So here at University of Sydney, we've got backgrounds in mechatronics and space engineering, and it was a good opportunity for us to investigate a payload which we could integrate into the rocket, but also had some type of, as an experimentation platform, that also had some link to space engineering. So we looked into the opportunity that a rocket can provide. When it reaches close to apogee, it may experience a very short period of quasi-microgravity. So we investigated this and decided that we could come up with a payload to utilize this environment, this unique environment, and actually perform or demonstrate an attitude determination control system in action within this rocket. So the payload is essentially just that. It is a small satellite, and we'll get into all those details, which will be aiming to demonstrate its attitude determination control system inside the rocket using some visual observation. So given the conditions of the quasi-microgravity and the fact that we are building and designing this payload for a sounding rocket, there are a number of challenges. The most important challenge that we've faced is the general size of this payload, the form factor restrictions, and of course, what type of environment it is inside of the rocket during flight. So the satellite itself must have full 3 rotational degrees of freedom, so that we can actually demonstrate that it can arrest these induced rotational energies as the rocket is twisting and changing its own trajectory close to apogee. The payload as well must fit within our rocket firetail, and that is of a 2U form factor with a minimum mass of approximately 8 pounds. So you'll see sort of how we had to design the payload according to those constraints. The period of quasi-microgravity is also quite short, so we wanted to find out how we could best observe the attitude determination control system in action with such little time, and make sure that we are actually counteracting the rotation of the rocket relative to the Earth frame or the inertial frame of the Pico satellite at launch. And finally, because everything is miniaturized, we're running this this system on a very small microcontroller, small batteries and small motors. So that was another one of our major challenges. To give you a bit of an overview of how this payload is actually operating in sequence with the rocket flight, prior to the rocket's launch, the rocket is sitting on the launch pad, and the payload itself is in a low power state. An accelerometer is built into the payload, and it's monitoring the acceleration up until the moment when the rocket launches. At that moment, we begin the countdown, and we'll be able to determine exactly when we approach this period of quasi-microgravity. And at that point, that's when we actually begin the demonstration. So I will say that up until this point, inside of our payload, where we've got this little satellite and a special rig designed to hold it, all of that is mechanically locked. And when we reach this microgravity, it will become released. Now, during the microgravity, we'll obviously try to demonstrate the Pico satellite, trying to counteract the rotation of the rocket, just as the satellite will do when it needs to detumble, and it will continue to do that as the rocket enters its recovery stage or its descent.
So the payload consists of 3 subsystems. There's the Pico satellite itself, which will be running the attitude control system on a microcontroller. The Pico satellite is mounted in a gyroscopic rig, and this, once unlocked, will give the Pico satellite 3 degrees of rotational freedom in which to move. The gyroscopic rig is in turn mounted to the launch vehicle integration structure. This is a 2U structure that has the roles of housing the satellite and gyro, physically interfacing with the launch vehicle, and coordinating payload operations during flight. So the integration structure frame is made of LaserCut 316 stainless steel. Steel was chosen for its strength as well as its density, as the mass of the steel was required to bring the payload up to the required weight of 8.8 pounds. Flight coordination electronics are mounted to the inside of the frame using housings 3D printed from PLA. The interior consists of 2 cavities separated by a steel plate. The upper cavity, shown on the left of this diagram, I don't know if you can see my mouse there, houses an Arduino Nano microcontroller, an inertial measurement unit, a micro SD card for recording inertial flight data, a cam stepper motor and associated stepper motor driver, as well as a relay switch and 3S LiPo battery. The lower cavity, shown on the right, houses the gyroscopic rig, as well as a camera module consisting of an Arduino Uno, an Arducam unit for recording video of the Pico satellite, and a second micro SD card module for storing the video data. This cavity also contains LED strip lights, which are shown down here in the purple, for providing adequate lighting for the camera. The Arduino Nano in the upper cavity will be running a virtual state machine, which will coordinate the activity of the other components throughout the flight. And this will be discussed in more detail in a few slides' time. The gyroscopic rig consists of 2 rings machined from 6061 aluminum. The rings use steel pins and radial ball bearings to rotate freely relative to each other. The Pico satellite is mounted in the rig using laser-cut acrylic attachments, which are free to rotate using the same pin and bearing method. The cam stepper motor previously mentioned, shown in the last slide, is used to, shown here in this slide, is used to lock the gyroscopic rig and Pico satellite in place until rotation is desired. The Pico satellite itself is constructed from 6 laser-cut 3mm acrylic faces. It contains an Arduino Nano to run the control software, an inertial measurement unit for measuring acceleration. For actuation, we're using 3 brass flywheels, 1 for each body axis, and each driven by a DC micromotor and associated motor drivers. Once the Pico satellite is free to rotate and free of disturbing torques, conservation of angular momentum dictates that any momentum developed by spinning the flywheels must be counteracted by a rotation of the Pico satellite frame. The control system will hence be able to manipulate the orientation of the satellite by driving the appropriate motor. The Pico satellite is powered by a 2S LiPo, and a single throw double pole switch is used to control when the satellite is electrically active. By using the rod of the cam stepper motor to depress the switch, which you can kind of see here in this slide, the satellite remains off until the desired moment when the cam stepper rod is withdrawn, similar to a remove before flight pin.
Okay, so to give you a bit of context as to how this controller works, the flight controller as we call it, we're utilizing a state space PD controller. So that's built into the right-hand side there, and it's got the typical feedback loop with the reference position. So this reference position, or the orientation that we want the satellite to remain in, is its inertial frame. And we have that relative to the Earth, or basically the rocket at the launch pad. Now, one thing that we found very interesting with this project that we wanted to capitalize on was investigating how well a Kalman filter would work for this project, particularly on a low-powered sort of microcontroller unit, and also just for our general interest in implementing it into this control system here. So we have an extended Kalman filter with the what I consider to be a very important stage of removing as much noise as possible from our noisy raw IMU data. Okay, so a bit of information about the Kalman filter. So the Kalman filter, sort of from a very high level, is intended to remove noise from noisy signals or from uncertain and biased data. The Kalman filter is designed to provide an estimate, a true estimate that we can rely on, and that estimate in itself is noiseless and most certainly certain. There's no uncertainty in that data. Now, I did some investigations into what type of Kalman filter could be run on this type of system, and an extended Kalman filter is very good, but it's typically designed for non-linear systems. So to keep it as simple as possible, I found an error state model Kalman filter, and it works slightly differently to a normal Kalman filter in that it actually estimates the error in normal readings rather than the whole reading itself. And then we can recombine that reading later on. So the readings I'm talking about, or the states that I'm talking about here, are angular orientation, which are inferred from the angular velocity measured by the inertial measurement unit on the Pico satellite itself. And I'll probably also just add here that we also have an additional algorithm here, which is using acceleration data from the same IMU to provide what we call an observation. And the Kalman filter in itself acts a bit like a control system, and it attempts to provide reliable and stable estimates of the state, which then feed into that PD controller. So I touched on this relatively briefly just before, but in terms of the operation of the whole payload relative to the sequence of the rocket's flight, at phase 0, the whole payload is in a low power state, and it's using an accelerometer, as Matt described, built into the integration structure to determine when the acceleration hits a certain threshold, so when the rocket launches. Once we hit launch, we've got a countdown, and it will determine when we release the Pico satellite and the gyroscopic rig so that we can actually do this attitude determination control system demonstration. So important part about this is that we keep the Pico satellite and the gyroscopic rig mechanically locked, and it also happens to keep the Pico satellite itself disabled. When we hit that point, phase 1, the linear actuator retracts, a switch is toggled, and that powers up the whole Pico satellite and attitude control system, as well as allowing it to freely rotate. And then during phase 2, we'll have a camera recording this whole event inside the integration structure. We want to see this Pico satellite arresting any imparted rotational energies, and hopefully we'll see it try to maintain a relative orientation to the Earth or the rocket when it was on the launch pad. We expect it to continue as well. With a lifetime of around 10 minutes, this Pico satellite should continue to run its algorithm, its ADCS, up until the point where we make a safe recovery. All right. Thank you very much for listening, everybody. Very happy to answer some questions.
All right, fantastic. Let's start questions.
Have you done any analysis to make sure that you can react quick enough?
Yes.
Do you have any? Okay.
It is a very good question. So we expect that we can, in fact, counteract the rotation of the rocket in both the sort of Z rotation as well as any type of heading or heading angular change. It will be fast enough to react, to our calculations, but we weren't sort of expected to make any sudden changes. What's important for us is, you know, through this video footage that we're going to take, that we will see the Pico satellite definitely making some positive change against the rotation of the rocket. We sort of understand that just as like normal satellites do when they're launched out of their launch vehicle, that they may take hours to hit a stable attitude.
Okay, and then you are pulling the pin, if you will, to let it go into its 3 degrees of rotation at a timed event and not at a measured apogee. Is that correct?
Yes, that's correct.
Okay.
So yeah, the motors and the microcontrollers are going to need time to power up. So we've done, the flight modeling team has done simulations on how long it's going to take to reach near apogee, and so we want to trigger it a little bit before then.
Okay.
So I'm just a little behind, I think, on a few things. So let's just say you're going up and the body of the 3U rotates 90 degrees. So the Pico satellite has an IMU. It senses the start of that rotation, and the goal is that you're going to counteract that rotation so that your camera inside, which is part of the fixed body, right? It's going to see the relative rotation of the Pico satellite as the body rotates 90. The Pico satellite stays relative to gravity, right? And so what you're hoping to see is your camera watch that Pico satellite, and we're just talking one axis for simplicity, watch the Pico satellite rotate 90 degrees to counteract that body rotation 90 degrees. Do I have it right so far?
That's perfect. Yep.
Okay. So what are you using for truth? Do you have another IMU on the body of the?
Yes.
Okay.
So in the integration structure, we did mention that it was an accelerometer, but it is an IMU in general. So we're using that for orientation as well in the integration structure.
Got it. Okay, understood. Thank you. What else we got?
I want to see that one. That's going to be pretty cool.
Yeah.
And let us know when you fly.
Absolutely will do. We're looking forward to it as well.
And you already told us the mass was 4 kilograms. Did you tell us that already?
Yes.
Yeah, okay. Any other questions?
I don't think so. That was a well done presentation.
Yeah, thank you very much. Nice job, and good luck.
Thank you very much. We
Thank
appreciate
you.
it.
All right.
Thank you.
Good job, guys.